to do the usual kind of estimates we do for local cubic NLS. Maybe need something like this. Here's one theory. You asked. So in terms of estimates, the non-local term behaves exactly like the local term. However, it's essential to get the sign in the virial identity. Without the non-local term, you do not have the virial identity with the sign on the right side. Okay, so welcome back. Before the break, I gave you one example of a result below the threshold, because in the radially symmetric case there is no threshold, so all solutions are global. So now let me give you one, just to mention, one more result below the threshold. So we're still below the threshold. And now let's take equivariant. In particular, not essential, but let's take degree 1 equivariant.
Okay, for the radial symmetric case, do you still have the limit, the restriction that at 0 and infinity, it need to point to the long pole at some point?
No. So it's almost erased. Almost erased. But I imposed from the beginning, the initial data, that at infinity, at least in this sense, I tend towards the North Pole. But there is nothing pushing it to the South Pole. So this is just boundary condition at infinity. There is no boundary condition at the origin. That's only in the equivariant case. Because in the equivariant case, you have a special axis of symmetry. And so the North Pole and the South Pole are special. In the radially symmetric case, there's no special point. So you just pick one. Good question. Back to the equivariant case now. And we are below the threshold. And we pick the boundary condition at infinity to be the North Pole. Now we are below the energy threshold. So we don't have enough energy. It's a topologically trivial boundary condition, and energy no bigger than twice the energy of the harmonic map implies that you cannot form. So I stated this as a conjecture, so let me state it again. So in this situation, conjecture is that when the energy is below twice the harmonic map energy, symmetric case, as I showed you, you don't work with the original equation, but you work with this derived equation for this function Q, which looks like a nonlinear Schrödinger equation. So this function, which is the representation of the derivative in the orthonormal frame, that's the function which scatters. So it's the Q function which scatters. So whenever I say scattering in these problems, it usually means that it's the representation of the spatial derivative of the function in orthonormal frames. Those functions which do the scattering. So scattering, if you don't know, scattering means that the solution at time infinity behaves like a solution of the free linear Schrödinger equation. That's what's meant by scattering. So you don't feel the nonlinearity. I just realized I'm supposed to put on the sky. Once again, in the one equivariant case with the topologically trivial boundary condition, the conjecture is that if the energy is below twice the energy of the harmonic map, you should expect global well-posedness and scattering, and that's because you don't have enough energy to form a non-trivial harmonic map. To form a harmonic map, I have to connect the two poles. I have to go from here down to here. That costs one energy at h, but because of the boundary condition, I have to come back. That costs twice the energy of h. So I don't have quite enough to go down and back again. So therefore, you expect global well-posedness. This is the picture. That's still open. So let's call it an open question. But there is a partial result which I want to mention. Due to Bldg, Ionescu, Koenig, and Takaru. 2012, which goes halfway. So their theorem is that halfway, energy below one energy of the harmonic map, then you get global well-posedness and scattering in the sense that I mentioned earlier. So in their situation, you only have enough energy to come down just to the equator, and then you have to go back up again. So these are maps. They're only covering one hemisphere. It can't cover the rest of the sphere. Okay, I'm not going to try to give any kind of sketch of this proof, just say what the ingredients are. So in fact, it's similar to what we just discussed, similar to what I did in the radially symmetric setting. However, it's much more complicated to do the orthonormal frames in the equivariant setting. I'll show you that soon. But that's what they do. So they do frames, express derivatives of the map so we're in the equivariant setting, so I remind you what that means. It means the map is of this form. I'm there as well. Okay. So again, they express derivatives of this function in the orthonormal frame.
again using a version of the Coulomb gauge, like we just saw. Again, they use the concentration compactness approach of Koenig and Merz. To reduce matters to showing non-existence of some kind of minimal non-scattering solution which has extra compactness properties. Together with, like we just saw, virial type identities, but which are more complicated virial type identities than the ones I wrote on the board before the break. And the fact of the matter is that the virial type identities that they get, they lose their sign once the map starts to cover below the equator. This is the reason for the restriction on the energy, which lose their sign if the map goes below the equator. So if you're looking for open problems to work on, here's another one. You have to push this off the equator. For this, you would need some other identity or something, some replacement for these virial identities. Sign. The conjecture, I believe the conjecture should still hold when you go all the way down to the south pole. Okay, so with that, I want to leave behind the below threshold business and go above the threshold, but only a little bit. So the next topic is to go slightly above the threshold. Salts. Okay, and again, we don't really know anything on this problem except in the equivariant setting. So I'm going to stick to M equivariant Schrödinger maps with energy a little bit above the harmonic map energy. Okay, so the picture is this one. So now it's non-trivial boundary conditions. So the south pole at the origin and north pole at infinity. And within this class of maps, you have the harmonic maps. So here's one, for example. Remember that they come in a two-parameter family. They live at all scales. And also there's a rotation parameter, which you don't see in this picture since I'm plotting the third component. So now we're considering energies which are a little bit above. So the energy of the harmonic map, as we saw last time, is the absolute minimum. It's the minimizer within this class. So to go a little bit above means you're close to a harmonic map, but not quite. So effectively we're taking small perturbations harmonic map as our initial data. Okay, so what are the results? Well, what's interesting here is that the results depend very much on this number m, on the topological degree. I'll give you results listed from high degree down to low degree. So let's start with the high degree. Which means 3 or bigger. In this case, under this assumption, solutions are global. And moreover, they converge to harmonic maps. In other words, there is some phase parameter and some scale parameter. Such that the solution converges in this sense, also in a scattering sense, in a space-time sense, but in particular, uniformly.
You see the energy comes through as energy goes.
The excess energy is scatters. So this is not the energy norm. This is L infinity norm. Okay, so this doesn't contradict energy conservation. You're absolutely right. The energy is conserved, but physically, you say it's radiated away. So locally, if you just look locally in space, you do not see the excess energy. It goes up. It's basically a scattering type of behavior. So we could say, another way to say it is scatter nearby harmonic maps. So the difference between the solution and the harmonic map behaves like a free solution of the Schrödinger equation, of the linear Schrödinger equation. It's a special property of the equivariant maps that you can control the uniform norm, the L infinity norm, by the energy, and therefore you can show that the difference goes to 0 uniformly. But it's really a scattering type behavior. All right, so this, in other words, this solution which starts near one harmonic map will converge to another, not necessarily this harmonic map, but a nearby one. Something like this. As time goes to infinity. Another way to say this is asymptotic stability. In this strong sense, the family of harmonic maps is asymptotically stable. So that's for high degree. If we drop the degree by 1, the picture changes in some way, and we don't have many results. In fact, the only comparable result we have is not for the Schrödinger map equation, but actually for the heat flow. So for heat flow, there's a similar statement, but different. So solutions global still. There's no singularity formation. And the harmonic map family retains this stability problem, stability property. In this sense, that there's a time-dependent phase parameter and a time-dependent scale parameter. And now, because this is heat flow and not the Schrödinger, I can really converge strongly. So I can consider this in the energy sense. The harmonic map family is stable in this sense, but we lose control over the parameters. For example, it's possible for the scale parameter to go to 0 as time goes to infinity. That would be behavior like this. Time goes to infinity. If you like, you can think of that as an infinite time blow up, or a singularity formation at time infinity. I'm not saying this happens for all data, but this happens for some data. For some data. Okay, so this, if you like, is infinite time blow up. Unfortunately, we only have results for heat flow. This is another open question, so open problem would be for m equal to 2, global well posedness, okay, GWP for the Schrödinger map. Let me call it Schrödinger map sub m for n equivariant. So this is Schrödinger map sub 2, or degree 2 equivariant. That's an open problem. And so is the construction of these infinite time blow-up solutions. This kind of behavior. I think maybe it should happen for the Schrödinger map, but we don't have a proof. Infinite time blow-up. Or what did I call it? Yes, blow-up. So those are open problems. Okay, I should say this is work, these two things here. This is work of a few years ago with Nakanishi and Tsai. Okay, so that's high degree is good behavior, asymptotic stability. Degree 2 seems to be some kind of borderline behavior. There's no finite time blow-up, but you can have infinite time blow-up. And then in degree 1, you can have finite time blow-up. May occur. this statement is already classical for the heat flow. So for the heat flow, the possibility of finite time blow-up was established by Chang Bing Ye in the 90s, I guess. And the reason this is relatively easy, well, I don't want to say easy, but easier for the heat flow, is that for equivariant heat flows, there is an even smaller symmetry subclass, which is preserved by the heat flow but not preserved by the Schrödinger flow, sometimes called co-rotational, for which you can reduce the heat flow equation to a single scalar parabolic PDE. And when you have a scalar parabolic equation, you have a bunch of other techniques available to you. You have maximum principle and comparison principle. So this is a comparison principle argument, in particular, a subsolution construction. So they gave a very clever construction of a subsolution which blows up in finite time, which by the comparison principle shows you that the true solution with initial data above this subsolution also has to blow up. Blow up in this sense, not in the sense of the map itself, because the map is bounded, but in the sense of the derivative at the origin becoming steeper and steeper. Derivative going to infinity at the origin. But then this was proved for the Schrödinger flow, or Schrödinger map, sorry. So let's call it 1 here. By Merrill, Raphael, Romiansky, more recently. Where, of course, in the Schrödinger case, of course, you don't have anything like a maximum principle or comparison principle available to you. So they constructed solutions which behave like this. So again, like this situation here. Some time-dependent phase parameter and some time-dependent scaling. Which converge at the blow-up time, something, let's say V star. Energy sense. And where this scale parameter goes to 0 in finite time. So this scale parameter behaves like this. Very difficult, very delicate construction of blow-up solutions in the Schrödinger case due to Merrill, Raphael, and Romiansky. So you can see that the behavior depends on the degree. High degree, it's asymptotically stable. Low degree, you can have finite time blow-up. And it seems like degree 2 is in between. You can have infinite time blow-up. But this has only been established for the heat flow. We don't have it yet for the Schrödinger case. So what I'd like to do is spend a few minutes giving you some flavor of how this asymptotic stability type is also proved. So let's do a very rough sketch of this m greater than or equal to 3 asymptotic stability. Okay. Let's start with the equation. Remember, what is the equation? So we're talking about the M equivariant Schrödinger map equation. Looks like this in terms of the function v. This is the radial Laplacian, or covariant radial Laplacian, and then we have the term coming from the angular derivative, m squared over r squared. Where's the form? There it is, up there, although that's for m equals 1. In general, we have an m. You take theta derivative, you get the matrix R coming down twice. So we have R squared v. And then to make its covariant derivative, I have to project back onto the tangent space. So that's how the equation looks before you make any frames. And we're talking about initial value problems. So we're going to specify some initial data. And the condition on the initial data is in terms of the energy. So the condition is that energy of V naught, of course energy is preserved, so I can call it energy of V, is a little bit above, but only a little bit above harmonic map energy. Let's call that delta squared. That's a small parameter. Okay. So we are trying to prove asymptotic stability. We are trying to prove that the solution, which we know begins close to a harmonic map, stays close to a harmonic map, but maybe with time-changing parameters, and in fact ultimately converges to some harmonic map. So anybody who's ever worked on stability problems will recognize how the argument begins. It begins with some kind of modulation. In other words, we're going to write our solution in two pieces. We want the harmonic part, harmonic map part, and a small correction. Okay, so how do we do this? Well, we have to allow the harmonic map parameters to vary. So here's the phase parameter. Here's the scale parameter. And here's the error term, or this term which is supposed to be small. The thing is, we have to remember that this is a geometric problem, so that this is not the usual function. It's a map. And we're taking one map, unit vector, and we're trying to write it as a small perturbation of another unit vector. When you make a small perturbation of a unit vector, you should decompose that unit vector. You could decompose the perturbation into the tangential and normal components. And the main contribution should be tangential. So we have the tangential part here, which we can write in some obvious basis. So let's remember that this function h has this form. This map h has this form. It's got no, until you do rotation, it's got no second component. So an obvious tangent vector is 0, 1, 0, or j. J 0, 1, 0. Okay, so I'm going to write the perturbation as something in the j direction plus something in the rotated j direction, rotated with respect to the harmonic map. So this is the tangential part. But there will also be a normal part, but that will be smaller. Assuming it's a small perturbation, this normal perturbation will be smaller than the tangential. So essentially, I can measure the perturbation away from the harmonic map by this function, or these functions z1 and z2, which I build into one complex function. We want to show, our goal is to show that this function z goes to 0 in some sense, so we should look at the equation for this function z. This is nothing complicated. You just take this expression, you plug it into the equation, and you spend some time, and you find what is the leading term, what is the linear part of the equation for this function z. And it looks like this. Of course, it looks like a Schrödinger equation. It has to. I mentioned this supersymmetric form of operators factoring into first order and the adjoint. That happens in all these equations. Here it is again. So this part here is the linearized operator. So called. We also we have, of course, many other terms. We have, remember, time-dependent parameters here, and the time derivative in the equation will also land on these time-dependent parameters. So that generates a term of this form. Just a moment. Yes. I'll say what everything is in a moment. And then a bunch of other terms which I treat as error terms. Let's call them nonlinear terms. Where so mu is just a combination of my two parameters s and alpha. Turned into a complex number. Mu dot means the time derivative. And then what is this linearized operator? Well, this L, first order operator dr plus m over r h3. h3 is the explicit function which appears in the third component of the map. Or another way to write it is like this. And finally, this notation with the S, whenever I write an S in the superscript, it means I have to put in the scaling. So the notation is, for example, H1S equals H R over S. H1 R over S. And LS is the corresponding operator with rescaled guys here. So on. That just indicates that the variable is scaled. Notice that from this form of the linearized operator and this form L, you can see immediately what the kernel is. So the kernel of the linearized operator is just the kernel of L, which is just this function H1, which is the first component of the harmonic map. And again, anybody who's worked on this kind of problem or looked at this kind of problem will recognize, of course, that there had to have been a kernel in the linearized operator. Because whenever your original problem has some kind of symmetry, invariance, in this case we have two, we have scaling symmetry and phase symmetry, the linearized operator always has corresponding elements in the kernel. In this case, since we complexified, it's one complex dimensional kernel corresponding to two real dimensional kernel. This comes exactly from the two invariances, a scaling invariance and a phase invariance. Okay. All right. So that's an important observation about the kernel, because you can see if you look at the linearized equation for the error term, if the linearized operator has something in the kernel, then that's a solution of the linearized equation which doesn't decay. We want everything to decay to 0, so that's an obstacle. And so we have to remove this kernel somehow. The way we remove this kernel is usually by orthogonality condition. More precisely, what do we want? We want Z to go to 0 in some sense, and we want the parameters to converge to some limiting value. In the complex plane. That's what we're trying to prove. That would correspond to more or less to this statement here. All right, how do we choose, when we do this decomposition, how do we choose which alpha and which S? How do we choose which harmonic map out of the whole family to linearize around? And the answer is by orthogonality condition. So we choose mu of t at each time by imposing, and again, this will be very familiar to anybody who's done stability theory, by imposing an orthogonality condition. Z orthogonal to something. And for convenience, whatever that thing is, I should rescale it. Some function. We'll choose the function later. Okay, so what happens when I impose this orthogonality condition? Well, now I can differentiate it with respect to time and use my equation. I'll get 0 on the left-hand side. Take the inner product of my equation with this function. If I ignore for a moment the fact that this depends on s, which is time dependent, if I ignore that for a moment, then on the left-hand side, I'll get 0. The first term on the right-hand side, I will get something non-zero. I will get this. Moving the adjoint to the other side of the inner product, I'll get this. And then from the last term, I'll get mu dot. And then error terms will come from the nonlinear terms. So roughly speaking, let me just write it this way. So nonlinear terms in Z will have Z squared type behavior. Okay. How do I choose this orthogonality function? Well, for one thing, I want to get an equation that describes the dynamics of my parameters. So I want this to be non-zero. In fact, why not just normalize it to be 1? Again, just set aside the fact that S is time dependent for the moment. And then the best I could hope for would be to remove this term altogether. So then I'd have an equation which says my parameter derivatives are quadratic in Z rather than linear in Z. This should be much smaller. And it's pretty simple how to kill this term. You take phi in the kernel of L. We know what the kernel of L is. So the natural choice would be to take phi equal to H1, which is the kernel of L. That would remove this term. And I'd have an estimate of, roughly speaking, of this type. Let's write it this way. Quadratic in Z. So this seems like a good choice. Why didn't I do this from the beginning? It's because this doesn't quite work, at least for n equal to 3. So this doesn't work. For m equal to 3. I'll come back to that in a minute. Okay. So that's the linearized equation and the orthogonality condition. All right, so second step. Now, let's suppose we were in this situation, good situation, where we have an equation saying the parameter dynamics are small if Z is small. So then we want to go back to the Z equation and estimate the Z equation to show that Z is going to 0 in some sense. That's a problem. It's a problem for several reasons. One, as I said before, this operator here has a kernel. And whenever your operator has a kernel, it's hard to get decay estimates or dispersive, any kind of decay estimates for the evolution. Of course, you can project out the kernel and hope that you get decay estimates for the projected equation. But that's something that's pretty hard to prove in one specific Schrödinger type evolution that's given proof. So there's a better way. And the better way is, like we saw before the break, instead of looking at this equation directly, we look at a derived equation using orthonormal frames. So this is frames again. Only it's a little bit more complicated than it was in the radially symmetric setting. So I'm not going to write it out. I'll leave it as an exercise. All right, so let me just show you how to set it up. So just like we did before, we want to take a unit vector in the tangent space, unit. And again, like in the radially symmetric case, satisfying so-called Coulomb gauge, which in this setting is just a parallel transport condition on the unit vector field. And now we're going to express certain derivatives of the map in this orthonormal frame. Okay, but before I say exactly what we're going to express, I realize I should have said something first. So probably this is going to be, okay, this can be 2, but I have to insert 1.5 quickly. So 1.5, let's go back to the energy for a moment. And remember, the integration by parts we did a long time ago, which looks like this. So in this case, I'm talking about a map which goes all the way from one pole to the other pole. So the number that goes here, I guess, is 2m, if I remember correctly. Okay, 2m, but more precisely, I can call it, why don't I call it what it is, which is the energy of the harmonic map. And remember that, so let me subtract energy of the harmonic map from both sides. And remember that our basic assumption is that our energy is slightly above the harmonic map energy. So we call this quantity the delta squared, less than 1. So what we can see from this this expression is that there's a natural quantity to try to work with, which is this quantity in here. So I'm going to call this guy W. W is a natural quantity because it's small in L2. So by this energy argument, W is small in L2. Okay. I guess I might as well write the equation now in terms of W. All right. So let's go back. Okay, I guess this is 1.75. Let's go back to the equation. Here it is on board. And let's factor it. Now let's see. I claim that I can take this quantity on the right-hand side and factor it in the following way. So here I put the quantity W. And here I put dr plus 1 over r plus m over rv3. Okay, maybe this is an exercise. Minus. This is exercise. So this is the quantity W. So now from here I can compute an equation for W. So let's differentiate W covariantly with respect to time. Now what happens? So here, when I put the dt here, I can exchange the covariant derivative with the regular derivative. So that's good. Here, I should remember that another way to write this quantity here is as pk, which is like this. When I differentiate this with respect to time, all I will get is minus v3 dt. Okay, so this is dr plus m over rv3 dt, I believe. Yes. And now we go back to the equation, use the fact that J commutes with covariant derivatives, and we get the following expression. Notice that this operator is the adjoint of this operator. So again, we get this so-called supersymmetric form. Where this dv, should I call it dv? No, let me, okay, call it dv. So dv, by definition, is this operator. Here we see, again, we see the geometric structure. These equations have a lot of structure. Okay, now finally I can go back to frames. So which tangent vectors do I want to express in the Coulomb gauge? Well, I want to express this one. So let's call Q the coordinates of W in this frame. All right, so the philosophy is we want to express all the spatial derivatives in frames. Here I have a radial derivative sitting here, dr. But I also have an angular derivative. But because it's equivariant, the angular derivative became this guy. So really I want to express radial derivative and angular derivative in frames. So I've done W, which means I should also do this guy. So I'm going to also express this quantity JRV in the frame. Let me give this complex function a name. Let me call it nu. Okay, so we express these quantities in frames. And now here's the big exercise for the brave students. one comes with a warning. So you are going to use this equation for W, this nice supersymmetric expression, and these frames. Similar to what we did for the radially symmetric case, but now it's considerably more complicated. And you're going to derive this equation for the function Q. And it's some kind of nonlinear Schrödinger equation. This operator, and again, the linear part here comes in supersymmetric form. LV is just the operator dr plus m over r. What is it? I guess it should be V3. Yes. And the nonlinear potential has this form. Okay. So again, this is superficially at least is similar to the radial case we saw before the break. I have some kind of nonlinear Schrödinger equation here. Here I have something a little more complicated than I had before. And also here I have something more complicated than I had before, but it also has this non-local behavior. But it's essentially, you could say it's essentially cubic. So this is again some kind of nonlinear, non-local, cubic Schrödinger equation. But there are a couple of important differences. This is not a self-contained equation anymore, as it was for the radial case. You can see that V3 is appearing, so the map itself, one component of the map is appearing. And also this nu is appearing, which is how we express the angular derivative in the frame. So this is not self-contained. It's not enough just to study this equation. This equation is coupled to it's really coupled to this one. But we use it for estimates, so it's a way of getting a priori estimates. But there's one interesting feature that I want to point out, which is kind of what makes everything possible here. If I look at this operator, this one, in its so-called supersymmetric form, this guy, so V3 is the third component of the map. And supposedly, what I'm trying to show is that my map is always close to a harmonic map. Right? So that means the third component of V to leading order should be the third component of H. So this is approximately, did I write it? Yeah, it's approximately this L over here. So for V3 close to H3, this is approximately LL star. So notice what happened at the linear level when I passed from the original equation for the perturbation to the derivative equation expressed in frames. The main thing that happened, most important thing that happened, is that the linearized operator changed from L star L to LL star. They got switched. So in other words, in going from Z to Q, L star L got replaced by LL star. And that turns out to be extremely important because this guy has a kernel. And so without extra conditions, the evolution cannot decay. This guy has none. And moreover, has a repulsivity property. I can write, in fact, explicitly what it is. It's this operator. Some kind of a Schrödinger operator. With a potential. Here's the potential. And I claim that this operator is, as a Schrödinger operator, is repulsive. In the physical sense. So in the sense that, in the quantum mechanical sense, that this potential is pushing everything away from the origin. Let me make that precise. Here's a lemma. This is a lemma which gives so-called Strickhardt or space-time estimates for the Schrödinger evolution corresponding to this operator. So this will be familiar to anybody who's studied Schrödinger equations, I guess. So if you look at the Schrödinger evolution for this operator, you have estimates of the following type. So this is time, this is space. This is for solving the linear initial value problem. It says that L2 initial data, the corresponding solution satisfies these space-time estimates. In particular, since I have something which is L2 in time, that implies some kind of decay as time goes forward. So this is a standard dispersive decay. And there's a corresponding one for the inhomogeneous problem. The Duhamel term looks like this. Which again will look very familiar to anybody who's used to these Schrödinger equations.
But that is the endpoint thing.
That is endpoint, yes. In fact, double endpoint. So I have L2 here and L2 here if I want. So that's right. So that's a good observation. These Strickhardt estimates are even better than what you get for the Laplacian. Just the usual Laplacian in two space dimensions. And the reason for that is that I'm radially symmetric. Well, equivariant, but radially symmetric. Although that's not enough to get double endpoint, but I have this. So it's this guy, this extra repulsivity at the origin, which allows us to have actually this very strong so-called double endpoint Strickhardt estimate, where you have L2 in time. With the experts. So these are very good space-time estimates for this Schrödinger operator. Okay. Let me give just a couple of lines about how these Strickard's estimates are proved for those interested in such things. Just a sketch of the proof of this lemma. So the first ingredient is a Kato type smoothing estimate. Which is a weighted estimate. So if I take this inhomogeneous Duhamel term, so I have this 1 over r weight, and measure that L2 space-time. That should be bounded by the opposite weight times the source term, also L2 space. All right. So this can be proved by a resolvent estimate. In other words, instead of looking at the Schrödinger evolution, you look at the elliptic problem corresponding to L star. You invert L star minus lambda. And this resolvent estimate just comes from an integration by parts. This comes from some work of these people. Lots of names. Okay, so the key is to get the resolvent estimate by suitable integration by parts. And once you have resolvent estimate, you can convert to Kato estimate by Plancherel theorem in time. So that's the first ingredient in these estimates. Second ingredient is the corresponding Strickard's estimates without the potential. So this is Strickard's estimates, including this double endpoint. So by Strickard's, I just mean these estimates. For this guy on radial function. This comes by some variant of the proof of the endpoint Strickard's by Kiel and Tau. Something like that. Okay. So now here's a good exercise for students. Put these two ingredients together to get the strict. Kato for this operator plus double endpoint Strickhart's for the operator without potential implies the double endpoint Strickhart's. For this operator. It's not so bad. You are comparing an operator without potential to one with a potential. You write down the Schrödinger equation. You put the potential term on the right-hand side. Use this guy. And then use the Kato estimate to control what you get on the right. It's a good exercise. Okay, so that's space-time estimates. And given these space-time estimates, for the linear part of the equation for Q, you can see that there's some hope, certainly to control the nonlinear terms. As long as the coupling, this V3 and this nu, which bring where is it? Which bring the Z back in, as long as that doesn't destroy things. One has to be careful, but at least there is hope. Yeah. So we can hope for some estimate of this form, Q as measured in these space-time spaces. Can be controlled by the L.2 norm of the initial data. Remember that Q is a coordinate representation of W. W is small in L2, so therefore this is small. Okay, you have to do many things to get to such an estimate, including controlling the nonlinear terms. But, we can't go into all details here. Okay, so where are we? That was step 2 was estimating the derived equation. Step 3. Now we have to go back to Z. So we need to recover so we went from the original map to Q. Now we need to go back. More precisely, we need to recover Z, which we said was orthogonal to some function, yet to be specified, maybe H1, maybe not, from Q and the parameters mu. So basically, we're doing a coordinate system in a neighborhood of the family of harmonic maps. I'm expressing the perturbation away from harmonic maps, which is this guy, in terms of this derived quantity Q and the harmonic map parameters. Okay, so this is a little bit tedious, but basically, at the linear level, if you look at how Q and Z relate, ignoring all nonlinear terms, Q is, the leading order is Lz, where L is this operator which has appeared everywhere. And so what we're trying to do here is we're trying to invert L on the spaces where we want Q to live, especially L2 and L infinity. And so I want to try to invert this guy from L2 and L infinity into a space where Z lives, orthogonal to the given function phi. And here's the lemma which gives the bounds for that inverse procedure. In L2, that's the energy space. We get these norms of Z controlled by the L2 norm of Q, provided the orthogonality function is integrable. Okay? And we have good mapping properties for the inverse. So that's at the level of L2, at the energy level. At the level of the Strickhards, the endpoint Strickhards, the L infinity, similar. But we need more localization on the orthogonality function. I'm not going to prove this law. Let's just use it. Okay, so now here's where the problem comes. I said before that the natural choice of orthogonality function I'd like to make is H1, the function which is in the kernel of L, because then I get this behavior here. So let's note that H1, I wrote an explicit formula for this function before. Its asymptotic behavior in space is like this. It decays like r to the minus m. So this quantity is finite. Well, what's the borderline? The borderline case is m equals 3. So m equals 3, this is 1 over r cubed, this is 1 over r squared, not quite integrable in two space dimensions. And so if for m equals 3, I either have to avoid this estimate or avoid this choice. But at least for higher m, it's okay. So if m is at least 4, I'm in business. And so what can I do? I can control z. Well, what I'm really interested in is the parameters. So I can say that mu dot I want to show that mu converges. So what I really want to do is integrate mu dot. So I need an estimate on its L1 norm. Mu dot is, if I can make this choice, mu dot is z squared. So I can bound this by certain norms like this of z. Take this one, for example, which I can then bound by q. Oops, wrong way around. Sorry. What have I done? I need L2. And then I'm done. I have a global bound on the derivative, integral of the derivative of u dot, so u converges. doesn't quite work for m equals 3 because I lose this estimate if I take phi to be h1. So instead, I choose some other phi, not h1, some other function for which this is finite. And so I live with the fact that in the equation for mu dot, I have a term which I can't integrate. This guy. This guy is the term which is linear in z. It's gone if I can choose phi to be h1. If not, it's still there. Otherwise, I have the same line of inequalities. Happy. Another problem is this guy. This guy turns out can be written in some kind of normal form, so to say, which just means, it's a fancy way of saying that the leading order, this itself is a time derivative. So this is dt of, approximately dt of something. Doesn't really matter for the sake of this presentation what. So let's just say it's some other function. Which means I can group this together with this mu and have a new parameter whose derivative is integrable and which therefore converges. And so to understand the behavior of mu, I just have to understand the behavior of mu tilde. And it turns out that mu tilde goes to 0. So it doesn't do anything anyway. So it's fine. It's fine. This is fine. The only last remark I want to make on this result is that when you go one lower down in degree is 2, and now we have to restrict only to the heat flow. We can't do the Schrödinger case. It's really exactly this normal form here, this guy, this correction to mu, which is driving the infinite time blow up that I mentioned. So roughly speaking, u of t, this mu tilde, I'm sorry, of t, this normal form correction, behaves like this function. Okay, so this is the initial value of the function q. Q is an L2 function. And so if you think about putting an r next to the dr and a 1 over r in front and doing a Holder inequality, to use the L2 bound, it just fails. So you have the integral of 1 over r dr up to root t. So as t goes to infinity, you lose control of this. So that's how you can drive. You can use this to drive, say, mu of t to minus infinity, which is the same as s of t going to 0. So that's the infinite time blow-up. Okay, so that's what I want to say about the slightly above the threshold dynamics. So that's the dynamics in a neighborhood of the harmonic maps. Basically, we know some things that happen, but we don't know everything. So when the degree is high, you get asymptotic stability. When the degree is 1, you can have finite time blow up. When the degree is 2, we have no result for the Schrödinger map. So that's an open problem. We only have some insight comes from looking at the heat flow problem, which suggests that infinite time blow-up is at least a possibility. We have no proof for the Schrödinger case. Any questions before the last subject for the day? So we did below threshold, we did slightly above the threshold. Now the question is to go far above the threshold. Topic 3. Okay, this is more or less completely open. To describe the dynamics far above the harmonic maps, this is another open problem. For the Schrödinger map, even in the equivariant case. So let me explain maybe a little bit why it's open. So suppose you wanted to describe the dynamics at higher energies. A natural starting point would be to characterize the ways in which a possible singularity could form, or a blow-up could happen. And the natural way to do that is to try to copy the harmonic map heat flow literature on this, which is classical. So the starting point would be to characterize blow-up as for the heat flow. For example, Struve's work. In the following way. So a blow-up would happen only through energy concentration. So some non-zero amount of energy concentrating at one point in the space, which would in turn imply a bubbling. In other words, the solution behaving like a harmonic map whose scale is going to 0. So roughly speaking, like this. So concentrating harmonic map. As you approach the blow-up time. Okay, so this is well established for the heat flow. Interestingly, there has been remarkable progress on doing this for the wave map. So for equivariant wave maps, you can find in the papers of Ducaerts, Koenig, and Merle. Characterizations of blow-up as energy concentration. So there's been progress on this for the wave map, but not for the Schrödinger map. So there are several respects in which the Schrödinger case is harder than the wave case. One has to do with the nonlinearity. So that unless you're in a very special situation like equivariance, then no matter how you write it, your nonlinearity will have derivatives in it, spatial derivatives. And that's much easier to handle for the wave equation, which is second order in time, than for the Schrödinger equation, which is first order in time. One reason. The other reason maybe is that in the wave case, you have some extra structure having to do with finite speed of propagation and light cone structure, which you can exploit in a way that Schrödinger map. So this we don't have for now for the Schrödinger map. So what can we do? Well, one thing we can do is to try the case where this characterization is already very well established, namely the heat flow. Okay. So the motivation, since we had this characterization for heat flow, let's try heat flow first. This is something which is obviously much simpler than the Schrödinger case, simpler even than the wave case for certain. But still there are at least some similarities in scaling and so on between the wave and the Schrödinger case. So if you can understand between the heat and the Schrödinger case. So if you can understand what's going on for the heat, maybe it gives you some insight into the Schrödinger. So here's a result along those lines. So in fact, we're going to consider as I mentioned before, a symmetry class of maps which is even smaller than the equivariance class, a subset of equivariance, which is the corotational. So corotational, that's maps of this form. So I have a scalar function u. And here's the theta dependence. Okay, so this is M equivariant, but it's more than M equivariant. It's a special case of M equivariant, and a nice feature of this is that you reduce matters to a single scalar function. So then you have an equation of this form. So that's the heat flow equation written in for corotational map. going to do something slightly more general here. I'm going to put a factor in front. I'll explain in a minute. And so let's consider the initial value problem. For this now scalar nonlinear heat equation, radially symmetric. What's this G? So this G is a conformal factor. Since we're dealing with the heat flow now, we don't necessarily have to restrict ourselves to Euclidean space as the domain. We can consider other domains such as this G. So this G is equal to 1. That's a domain R2. But if you take the conformal factor like this, that's taking a compact domain S2. So that's maps from S2 to S2. Because it's heat equation, we can do this without too much pain. Okay, and now what are the maps we consider? Okay, picture is slightly different now because this U is not the vector field anymore. It's an angle. Okay, so instead of going from the North Pole to South Pole, this angle U should go from 0 to pi or pi to 0, something like that. So let's do it this way. Let's take it from pi to 0. So something like this. All right, and here's the theorem. Some recent work with a student. Okay, so we already know what happens if we're close to a harmonic map. So the harmonic map in this picture would go like this. And we also know that under these topological constraints, the minimum possible energy is the energy of this family of harmonic maps. Okay, we want to go up much above this in energy. So how far can we go above? Well, let's take energy. No bigger than 3 times the energy of the harmonic map. Okay, so I'm going to, harmonic map in this picture is a different function than the previous function. So let me give it a different name. Let me call it Q. And to be explicit, Q is, what is Q? Q is pi minus arctan of something. R to the power m with 2 in front. So this is the harmonic map, and again, it's scale invariant, so any rescaling of this is also a harmonic map. All right, and the theorem says that under this energy condition, which is clearly well above the harmonic map energy, we have that the solution is global. And decays to 0. Not 0, I'm sorry. And converges to Q. So let me be more precise. Let's say that Q minus some rescaled version of the harmonic map. It goes to 0 in the energy sense. And this is, again, as in the previous discussion, I have to take the degree sufficiently high. So this should be m at least 4.
The 3D cube covers the energy for different n.
Yeah, it's not. So I didn't make it explicit here, but the Q depends on m. So maybe I should call it QM.
Same thing. Do you have an overlap with the energy for different harmonic?
You should think of the different m's you should consider separately because they are different symmetry classes. So once you fix the symmetry class and you fix the boundary conditions, there's only a one parameter family of maps, and they all have exactly the same energy. This energy is scale invariant, so no matter how I scale, this value of the energy is fixed. So it's a fixed threshold given m and given the boundary conditions. Okay, let me explain briefly why, well, maybe you can see why 3 times the energy. The point is that certainly I have enough energy to form one harmonic map, but under this condition, I don't have enough energy to form 2 harmonic maps, or if you like, a double bubble or a bubble tree. So that's the role of this condition. So, well, I'm going to need this picture. Bring this back down. I'll go over here. So this condition implies that if I do have a bubbling, where is it? Oh, I guess I erased it. If I do have a bubbling, it can only be one bubble. Bubble is just a harmonic map, so only one bubble can form. You can see that from here. So if I want to form one bubble, I have to go, say, from pi to 0. That costs me 1 harmonic map energy. If I want to form another one, I have to go, say, from 0 down to minus pi. That costs me 2. But then I have to get back to my boundary condition. So that would cost me 1, 2, 3 harmonic maps. Harmonic map energy, remember, is the most efficient way energetically you can go from one height on the sphere to the next height. So that's the reason for this condition. Okay. So I don't have time to go into details. Let me just make a couple of remarks. One is that there is a result of Grotowski and Chata gives a similar conclusion. But by different method, by maximum principle, by comparison principle. Our philosophy was to try to do things that can extend outside of this class of co-rotational maps, for which maximum principle or comparison principle type methods are not available. Okay, so what's the heart of the matter here? So the basic ingredient in the proof of this theorem is the following lemma. Okay, first, the name of the game is to rule out finite time blow-up, rule out singularity formation. And we know from the classical harmonic map heat flow literature that finite time blow-up has to occur through bubbling. So the goal is to exclude this possibility so this would be a bubbling. So this is a finite time blow-up through bubbling. So here's the harmonic map, which is concentrating. The scale parameter is going to 0. This is the weak limit at the singular time. Okay. And the tool to avoid this is the following lemma, which is kind of a stability or perturbations lemma. Which says the following. Suppose that W is some global solution of the heat flow. Heat flow M, that's this guy here. Which goes to 0 at infinity. Okay, so that would be something which has 0 boundary conditions, which just converges to 0 at infinity. Then I can find S hat epsilon naught such that the solution with initial data of the following form. So I want a concentrating harmonic map. The initial data for this global solution plus the initial data for this global solution plus something small. So the conditions here are S is sufficiently small, and the energy of this guy is sufficiently small. So if this is the initial data, then the solution is global and converges to some harmonic map. Certainly I don't have time to prove this, but this is actually some variant of what I talked about previously. So this is a variant of our asymptotic stability. Argument. I won't say more than that. Okay, so then how do we prove the theorem using this lemma? Well, apply the lemma. Suppose you have a bubbling like this. Apply the lemma with, so the global solution will be the solution emanating from the weak limit at the blow-up time. W equals the solution starting from the weak limit at the blow-up time. And, oh, why is this solution global? So this solution is global because after the blow-up, I have a blow-up like this. Some kind of concentration here. And what's left after the blow-up, the weak limit, will connect 0 to 0. And because of my energy condition, I used up one harmonic map energy forming the bubble. What's left is at most 2. And if I'm connecting 0 to 0, then it would take, to form a bubble, I'd have to go down once and come back up again. That would cost 2. And so now I'm below 2. So this is global. Since the energy is below twice the harmonic energy. And the small guy will be the difference here. And I choose this T close enough to the bubbling so that the conditions of the lemma apply. This difference is going to 0 in the energy norm, so I can make this sufficiently small. And moreover, the S is going to 0, so I can make this S of t sufficiently small to apply the lemma. I apply the lemma, and I get a global solution which contradicts the bubbling state. Okay, so somehow the idea here is simpler than what I wrote. You have two solutions coming from here and from here. This one is very concentrated, and this one is global globally bounded. And so as S goes to 0, these guys, they live on different scales. So when I add the corresponding solution, so I add this harmonic map to the solution coming out of this initial data, of course, the sum of two solutions is not a solution, but because of the scale difference, they're not interacting very much. And so the interaction in the nonlinearity is very small. That's what makes all of this work. Okay. That's all I have to say about the geometric flows. So that's it for today. Thank you for your attention.
Okay.